But as a bonus, I think we should probably do this one completely. Like, I know I've done one in the videos where we've done an eigenvalue eigenvector problem, but it's probably worth doing another one just so that we're all here together. So if you manage to answer this question ahead of me, go ahead and start doing the general eigenvalue eigenvector equations. There is another eigenvalue and another eigenvector. So see if you can find them as just kind of a bonus. And then I will take that up afterwards, and then you can compare your answer to mine, and we'll see, if you manage to get it. Okay, so depending on how much reading you've done, so I'm still going to give you a bit of time because I know this one takes a little bit longer, especially if you're doing it the hard way, like the long way, which is great because it's good practice. I think a natural question that you might have, which is like, why do we care, right? Why do we care about eigenvalues and eigenvectors? And there's a very real sense in which they're easily one of the most important things that you can possibly have about linear algebra, right? It's one of the most important things you can study in linear algebra. It's a little bit hard to see. We might have an opportunity to talk about them in a couple of weeks. We might be able to talk about Markov chains, depending on how our timing goes. And Markov chains are super important. They occur in almost every, like anytime you model something that changes in time, Markov chains are often involved. And they show up everywhere, but there's a very popular, very common place where Markov chains do actually show up. And I don't remember if I mentioned it in the videos, But Google, for example, uses eigenvalues and eigenvectors. When Sergey and Larry published the original paper that eventually led to Google, and basically they were publishing their PageRank algorithm, right? So I don't know if you ever thought about how Google works. It's quite complicated, right? Like if you plug in a bunch of words into a search engine, it then has to go out and try and find all the websites it can find on the internet, and then find the ones that are most likely to match the words that you put in, and then it displays them to you in an order that it thinks is the most relevant, and then the next most relevant, and so on and so forth. And that's actually a really tough technical challenge, right? As students who probably grew up with Google, I imagine it's easy to take that for granted, but it's actually a very tricky technical challenge. So the way they solved this problem is basically as follows. What they did is, if you imagine, when you go to a website, right, it often includes links to other websites, right? And so what they did is they created a big old matrix. And what this matrix does is it keeps track, the rows and the columns are websites. And what they do is they keep track of which websites link to other websites. So if the U of T website links to, the CBC website, 10 times, they'll put a little 10 in the row and column that corresponds to U of T and CBC, right? So they put a 10 there. And then the way the PageRank algorithm works is Google then will compute an eigenvalue eigenvector pair of that matrix, the matrix of all the websites on the internet. And the eigenvector, which has the biggest eigenvalue, is basically the first thing that you see in Google. And then the second biggest eigenvalue is the second thing. And then the third biggest eigenvalue is the third thing, and so on and so forth. And the fact that this works is, what was profound and special about their paper. But every time you use Google, and of course, PageRank has evolved since then, right? Obviously, it's gotten a little bit more customized. But, every time you use Google, you're using eigenvectors and eigenvalues implicitly behind the scenes. So that's actually how that works, right? So there you go. There is a insane, basically $1 trillion business, which was built on the basis of eigenvalues and eigenvectors. Yes, because in practice, it actually doesn't look at the entire matrix. This is part of the beauty of what they did, right? Is that the actual matrix is insane, right? It's gigantic. It's a billion by a billion size matrix. But it turns out you don't care, because most websites don't link to most other websites, right? There's a sense in which this matrix is very sparse. Most of it is 0, right? U of T does not link to a bunch of Mongolian government websites that. There aren't a lot of links there. So you can localize your matrix. Basically, you can cut out chunks of it, right? And then if you can figure out what the most relevant chunks are, you can make that eigenvalue, eigenvector calculation much, much quicker, right? Instead of actually computing the eigenvalues and eigenvectors of the whole matrix, right? So there are things that you can do to make that a little bit more sped up. Right? So yeah, obviously it's more complicated than that in practice, but eigenvalues and eigenvectors are an integral part of how the PageRank system works. Okay. Anyway, okay, so we're at about 60% now. I'm going to close it in about 30 seconds because I've given a fair amount of time to work on this, and we want to be able to grind it out. And yeah, also it's very hard. I've always found, and it's something I've always talked about, it's really hard to determine what takes a long time for a computer and what doesn't take a long time for a computer. You know what I mean? If you think about the average video game that a person plays, that's insane. It's absolutely insane. If you think about a first person shooter sort of thing and ray tracing, and the fact that, when you play a video game in 60 frames per second, your computer is calculating that picture 60 times a second, right? It's computing where everything is 60 times a second and showing it to you at a fraction of a second, right? It basically just redraws the page, right, in 1/60th of a second, and is constantly recomputing all of that stuff. That's insane, right? Computers are nuts. That's the entire point. Computers are absolutely insane in what they can do. Okay, so let's take a look at this. Unfortunately, not a lot of people participated, only about 2/3 of you. We are leaning towards A. A is absolutely the correct answer, so good job. Now, there's a fast way of doing this, and then there's a long way, and I think we should do both, right? So the fast way to do this is to say, well, if I understand what an eigenvector is, then, well, they've only given me 4 options. I should just see which of these vectors actually works. Okay, so this is question 7. Okay, so we were given this matrix, m equals 0, 1, -2, and 3. Okay, and we were given that lambda is equal, oh no, sorry, we called this A. Lambda is equal to 2. Okay, so remember the definition of an eigenvector is anything which satisfies this, right? AV is equal to lambda V. So in our case, we're looking for a vector such that this is true. Right? Okay, so what we can do is, first of all, if you wanted to, you could actually just plug V1 and V2 into both sides of this equation and come up with a linear system of equations. And in fact, for those of you who did writing assignment 1 or writing assignment 2A with the turtles, this is kind of what you were doing. Like, you may not have realized it at the time, but you were effectively solving an eigenvector eigenvalue problem. But anyway, so you can just start plugging them in and see which one works. So let's try A. So A said, this is the only one I'm going to do by hand because it's the correct answer. The rest I'll do by octave, just so we can practice doing octave a little bit. So if we do this and we plug this in, 0, 1, -2, 3, we plug 1, 2 into here, what do we get? So we're going to get 2, and then we're going to get -2 plus 6. So that's 4. And if you look at that, yeah, that is exactly 2, 1, 2, check mark, right? And there you go. That's it. It happened to be the very first option. And so, like that, we are done. Now, let me, here, I just want to make it so I can still see the question. Now I'm going to show you, we essentially did the dot product. Yeah, it depends on what you mean. So like here, this is the matrix product, right? Which is sort of built up by a bunch of dot products, if you want to think of it like that. Oh no, I just factored out the 2. Right? To get 2, 4. So I did, well, okay, so I did a dot product of this row with this column. That gave me the 2, right? And then this row with that column gave me the 4. So if you want to think about it like that, then yeah, there were 2 dot products and that's what gave me 2, 4. But that's how matrix multiplication works, right? Okay, so what I'm going to do is I'm going to plug the rest into octave. Because again, we like to, get a little bit of experience with octave and see how it works. So I'm going to check the other 3 options with octave. And just so that we can see it. What do you mean, what if the question is an essay? Like, what if we ask you to write an essay? Well, then, yeah, you probably can't use octave for that. Okay. So you can see I've plugged the matrix A into octave like this, okay? And I'm going to let V, so first of all, this is the answer we already checked. And what I'm going to do is I'm going to do A times V, that's equal to 2, 4. Yeah, that's exactly what we said. That is 2 times the original vector, right? Okay, let's do V equals 1, 1, right? Now let's see what happens when we multiply A times V. Ooh, what? Is 1, 1? Oh man, 1, 1 is also actually an eigenvector. Oh, no, but it's an eigenvector with eigenvalue 1. Do you see this? Does everyone see this? AV is equal to V here. Do you all agree? So 1, 1 is an eigenvector, but it's not the correct answer because the correct answer specifically says it has to have eigenvalue 2. So if this were the correct answer, then when we computed A times V, we would have gotten 2 times this out. So we would have gotten 2, 2. Do you agree? So it is an eigenvector. I'm certain we did that on purpose. But yeah, exactly, Brandon. Yeah, exactly. There are 2. And so I'll do it for you and I'll show you how you would have gotten these 2 numbers if you hadn't known this ahead of time. But yeah, that's why we did it. Now, V being 0, 0, you might be like, okay, well, this is 2 times 0, 0, right? And that would be a fair answer, except if you go back and you look at the definition of an eigenvector, eigenvectors are not allowed to be the 0 vector, okay? So you might argue that this is an eigenvector, except it's not by definition, okay? So by definition, we never let the zero vector be be an eigenvector. And then finally, if we do 2, 1, well, that's definitely not 2 times 2, 1, right? We would have expected to get 4 times 2 out. Instead, we got 1 times, or 1 comma negative 1. So it's not an eigenvector no matter what. Okay, does that make sense? And then, of course, you can cheat and you can just say, hey, Octave, what are the eigenvalues for this matrix using this command? And it will output a diagonal matrix. That diagonal matrix has the eigenvalues along the diagonal. So in this case, we can see that the eigenvalues are 1 and 2. And then it outputs these weird looking things. These are the correct answers. These are the answers we got. This here is 1, 1. This here is 1, 2. But they're scaled differently, right? They're actually normalized. These are both designed so that their norm is 1. We haven't talked about that, but that is the only kind of problem with using Octave for this, is that it has a tendency to write the vectors as unit vectors, and so they end up having weird like decimals in them and stuff. So unfortunately, we can't like avoid that, but you can use that to kind of sanity check your answers and see, oh, hey, did I get that answer correct or not? Now, let me show you how we would do this if we were actually just, if I just actually asked you to compute it, because I think, you know, we should do at least one of these, right? Yeah, I know, I had to switch over. I had to just switch my thing. Okay, so you should be able to see it now, right? Okay, so somebody tell me, what is the first thing that we have to do? So let's pretend we didn't know any of the eigenvalues and the eigenvectors. We had this matrix here, which we said was, what was it, 0, 1, -2, 3. And we want to find its eigenvalues. And okay, no, so the row reduction, this matrix does have full rank. So if we row reduce it, we'll get the identity matrix out, but that's not going to help us find the eigenvalues or eigenvectors. Agam, perfect, right. So we want to, first thing we want to do is find the characteristic polynomial. And does anyone remember what is the characteristic polynomial? So we'll call it P of lambda. The characteristic polynomial is what? No one remembers? Okay, yeah, okay. So Brandon, you are absolutely on the right track. So A minus lambda I, we want there to be a non-trivial solution. So Brandon, you kind of, that's not the characteristic polynomial, but you're exactly on the right idea. And Agam, you have it as well, but you need a lambda in there. So an eigenvector eigenvalue pair satisfies this equation that Brandon put up. And notably, because V is not allowed to be the zero vector, this needs to be this needs to have a non-trivial solution, right? Yeah, exactly. Beautiful. Yeah. So, and Abby, yes, you are absolutely right. That is A minus lambda I. Exactly. Perfect. So everyone, this is important to understand. The only way that this has a non-trivial solution is if this matrix is not invertible. Do you agree? Remember, invertible matrices have full rank because when you row reduce them, you get the identity matrix, right? So we need this to have infinitely many solutions. That's what we require. For it to have infinitely many solutions, its determinant must be 0. And so we take the determinant of A minus lambda I, and we want to figure out when that's equal to 0, right? Because we want that matrix to be non-invertible. Okay, so we're going to use, Abby managed to write it down for us. So it's going to be negative lambda, oops, that's not a lambda, negative lambda 1, -2, 3 minus lambda. And we know how to compute that, right? So we'll get negative lambda 3 minus lambda plus, oh, sorry, that's a 2 plus 2. So that's lambda squared minus 3 lambda plus 2. So that's lambda minus 2, lambda minus 1, right? And so the roots of this are exactly lambda equals 1 and 2, right? So the roots our lambda equals 1 and 2. And that's exactly what we found when we were just plugging things in and when we used octave in order to find the eigenvalues, right? Lambda is a fun word, absolutely, yeah. Okay, so that's how you find the eigenvalues. Yeah, exactly. Yeah, half-life, probably, do you mean the game or the chemical property? Which is obviously named after, the game is named after the chemical property. Yeah, okay, so yeah. And yeah, that's because when you actually do half-lives, you often do e to the lambda t, and the lambda there is the half-life, right? Like that is where that comes from. Okay, so now we have our roots. Those are our eigenvalues. Now, how do we find the eigenvector? So let's say we want to find the lambda equals 2 eigenvector. What do we do? Yeah, okay, Abby, absolutely. But where do we replace it? We want to put it in here, right? We basically want to solve it in here. So if we do lambda equals 2, what we want to do is we want to find the solutions to a minus 2i v equals 0, right? That's what we want to do. And that's, I assume, what you meant, right? When we replace lambda. So we actually want to find the solutions to this. And so if you want, what we kind of classically do, let's actually compute a minus 2i. So a minus 2i is going to be -2, 1, -2, 1. And then if I write this system as an augmented matrix, I'd write it with, my vertical line and 0, 0. And then, row reducing this is pretty easy. So let me just put this in RREF for you. Definitely the bottom row becomes zeros. And we get that, right? And if you wanted to use octave to do that, you certainly could. Remember, when you do this, you need to get infinitely many solutions. If you row reduce this matrix and you don't get infinitely many solutions, you did something wrong, because that's the entire point of the eigenvalues, is that they're going to give you infinitely many solutions, right? So when we parameterize this, so if we rewrite this as a system, we get x1 minus 1/2 x2 equals 0. Let's let x2 be equal to s, right? Remember how to do this? So we end up getting x1, x2 is equal to -1/2 s. And now here, back in the day, I was saying you didn't need to worry about pulling out the s, but in here you definitely do. Oh, sorry, this should be +1/2. 1 like that. Okay, so this is your eigenvector right here. Now, right, exactly, yeah. Okay, now, some of you might be upset and say, well, hold on, that's not what we had, right? We said above that 1, 2 was the eigenvector that went to lambda equals 2, right? So why are these the same answer? Why? Exactly. All we've done is we took the first eigenvector, 1/2 1, and we multiplied it by 2. Davin, exactly, we scale it. Any scaling of an eigenvector is still an eigenvector, right? And we don't distinguish them. We say they're ultimately the same eigenvector. So exactly what we could basically say, if you wanted to say it a different way, is that for any value of s, this is an eigenvector. And so if we had set s to be equal to 2, we would have gotten the solution 1, 2, right? But we could have used something else. If we had used s is equal to 6, we would have gotten 3, 6 as our eigenvector. No, there's infinitely many solutions, right? Because here's the thing. Look at this. So let's suppose that AV is equal to lambda V. Now let's multiply both sides by any number. Okay, let's call it C. So if we multiply by C, and that's just a real number, okay, that's not a vector, then I would get CV is equal to lambda times CV, right? So it says that if V is an eigenvector, then CV is also an eigenvector for any value of C, right? Because it still satisfies that same equation of A times the vector is equal to lambda times the vector. Does that make sense? So any scalar multiple of an eigenvector is still an eigenvector. We usually just say though that they're the same eigenvector, right? Because they are generated by the same solution of the homogeneous system. Agam, yeah. So we chose. Let me phrase that maybe slightly differently. We chose the number 2 to guarantee that A minus 2I would not be an invertible matrix, and because it was not invertible, that guaranteed that A minus 2IV equals 0 had a non-trivial solution. Okay, does that make sense? And I'm going to let you all check. So if we do the lambda equals 1 eigenvector, so that would give me what? Let me just look at what the original, well, whatever. I have the original matrix on a different screen. So that would give me -1, 1, -2, 2. So I'd want to row reduce this system, right? This is the one I want to find. So we'd get 1, -1, 0, like so. Again, that would give me x1 minus x2 equals 0. We'd say let x2 be equal to s. So we get x1, x2 is equal to ss is equal to s times 1, 1. And in this case, we would get the same, this is what we found, the 1, 1 vector. But again, any multiple of this would have worked as well. So 2, 2, 3, 3, pi, pi, -5, -5, any scalar multiple of this vector, except for the 0, don't multiply by 0, but any scalar multiply of that would work. Yes, Victoria. Yeah, so you're absolutely right. That does, I think, sound kind of confusing, right? In the sense that for each eigenvalue, there's only one eigenvector, but it can be scaled. So unfortunately, the answer to that question is also no. So let me put it this way. So let's say, I was doing a 3x3 system because it's the only way I could do things. And let's say that if I did a 3x3 system, and I think there is one in the notes, so you might want to check. But let's say I did a 3x3 system and I got this when I row reduced. Okay, let's say this was like lambda equals 5 or something. So I would get x1 is equal to 2x2 plus 3x3. We'd say like x2 is s, x3 is t, right? So in this case, when I write down my solution, I would get 2s plus 3t, st. And now when I split it into s's and t's, I would get s210 plus t301. So this means that in this case, this eigenvalue actually would have 2 eigenvectors. Okay, and those would be them. But yes, otherwise your sentence is correct. There is up to scaling. If I get something like this, there is up to scaling. That is the only eigenvector, right? But any scalar multiple of that vector also works. And so we kind of pretend that those are all a single eigenvector. Does that make sense? Well, no. Okay, so generally an n by n matrix has n eigenvectors always, or sorry, n eigenvalues. And the number of eigenvectors will depend on the eigenvalue itself. It very much depends on the matrix. So for some matrices, so for example, if I give you a 3x3 system, it's possible that you have 1 eigenvalue, 2 eigenvalues, or 3 eigenvalues. And then depending on those situations, each of those could have a different number of eigenvectors as well. So there are infinitely many scalars of an eigenvector. Yes, that's true, right? Because you can scale it by any real number, and there are infinitely many real numbers. Okay, so yeah, it starts to get a little bit complicated. It is impossible to tell how many eigenvectors an eigenvalue should have until you just go and compute it. Okay, so Jack, in your case of the 4x4, it is possible that a single eigenvalue could have anywhere between 1, 2, 3, or 4 eigenvectors. It is actually possible for a single eigenvalue to have 4 eigenvectors in the 4x4 case, but it could only have 1. Okay, and you don't know it until you actually go and you solve the homogeneous system. When you get into the mathematics of actually trying to figure out how many eigenvectors an eigenvalue has, it gets very, very complicated. Okay. And this is the sort of thing that they cover in like 247, which is the second year specialist linear algebra. That's where they start to cover that. So it's a very advanced topic. For you, I would say right now, everyone, what you're going to do is you're just going to try and solve the homogeneous system, split up your parameters like S and T, and whatever those vectors are, those are your eigenvectors. Okay. Now, there's not going to be very many situations in our class where multiple eigenvectors will occur for same eigenvalue. Okay, it won't happen very often. I mean, hell, most of the time we're not going to give you anything more than a 3x3, right? So there's definitely only so much pathological behavior that can happen. Are there any more questions about that? Is the eigenvalue what lambda is equal to? Yes, Curdy, yeah, exactly. Yeah, lambda is the eigenvalue. Okay, any other questions before I move on? Because I just want to make sure everyone's really okay with these eigenvalue, eigenvector questions. Okay, all right, here, let's go. Ooh, oh, too far, way too far. Here, let's do this one. Because we just talked about this. Okay, so I'm going to give you 30 more seconds or so. Okay, so let's take a look at this. Very good. The class is leaning towards B, and B is absolutely the correct answer. Hopefully, again, kind of just based off of what our discussion was, the answer was probably either A or B, because if you look at these two vectors, Parker's vector and my vector, one is just a scalar multiple of the other, right? If we take Parker's vector and multiply it by -2, that's equal to my vector, right? So if one of these is an eigenvector, both will be. And by the same thing, if one of them is not an eigenvector, the other one can't be either, right? So they're either both eigenvectors or neither of them is an eigenvector. So if we want to check if they're an eigenvector, we only need to check one of them. Now we could just check both of them anyway. Like if you wanted to do it that way, you could. So like even if you didn't know that, you know, the scaling of one worked. So we have, this is actually question 10. I jumped a lot. So we have A is equal to 7168. Right, and we've got VP is -1/2 1. We've got VT is 1 -2. All right, and we can just try them out. So if we do A times VP, let me give these little vector hats. So that's going to be 7168 times -1/2 1. And if we do that, what are we going to get? So -7 halves plus 1, so that's -5 halves. And then -3 plus 8, so that's 5. And yep, that's 5 times -1/2 1. Right? So it is an eigenvector. And then if we do AVT, so we get 7168. And then 1 -2. So we're going to get what, 7 minus 2, so that's 5, 6 minus 16, so -10. And yep, that also works. So even if you didn't recognize that they were both scalar multiples of each other, if you plug them in, you see, oh, look, these are both actually eigenvectors, right? No, I told you, right? The question said, Parker says this matrix has this eigenvector, and Tyler says that this matrix has this eigenvector. You didn't have to find it, because in some sense, if you just compare these two things, like let's say this, I did not find the eigenvalue ahead of time. So let's say that I got down to here. Yeah, let's just look at this equation. So let's say I get to here and I say, okay, is that related? What I'm going to do is I'm going to look at this equation, and I'm going to look at this equation, or this vector. I'm going to say, is one of these a multiple of the other, right? Can I multiply 1 -2 by something to get 5? And the only, if there's going to be an answer, it's going to be 5, right? Because what do I multiply the first number by? 1. In order to get 5, it has to be 5. And so that suggests that if it is an eigenvector, this should be true, and lo and behold, it is. Does that make sense? Right? And then if you do the same thing for the line above, like if you look at this and you look at this, you say, okay, are these is one a multiple of the other? And I would say, yes, they are, right? One is 5 times the other one. So in that sense, like if you actually know the eigenvector, if you know it's an eigenvector, it's not too hard to find the eigenvalue, because you just look at the input vector and the output vector and you say, is one a scaling of the other? And if it is, that scaling factor is precisely the eigenvalue. Okay. Right, yeah, the signs don't matter. Yeah, for sure. You could multiply something by -10. So for example, if we multiplied VP by -10, right, what would we get? We get like 5 -10, right? Totally also an eigenvector. We could multiply it by like pi, right? So we could do like pi VP, right? So we get -pi over 2 pi, also an eigenvector, right? Okay, direct messenger, can you expand on maybe what's confusing you? So do you agree that they're both eigenvectors? How do I know? So the point is that I don't. So the question is like, how do you know that these eigenvectors work? So the answer is that I don't know that they work. What I just did is I just plugged it in, right? So for this equation, I'm just going to carry out the multiplication and see if it works, right? So when I carry out the multiplication, I get negative 5 halves 5. And I say, are these two are these two scalar multiples of one another, right? Like, is there a number I can multiply the left by to get the right? And this one is not too bad. I can do it by inspection. I can see that, oh yeah, if I multiply that one by 5, this actually does work, right? Now, there's no guarantee that that's going to happen, right? So for example, let's just choose something totally different. So let's say I multiplied by 1, 1. I wanted to check if 1, 1 was an eigenvector. And I carry out this, and what do I get? I get 8, 14, right? And I look at 1, 1, and I look at 8, 14, and I say, is there any number I can multiply 1, 1 by to get 8, 14? And I say, no, that's impossible, right? Because I'd have to multiply by 8 so that the first number worked out and 14 so that the second number worked out. So this isn't an eigenvector. It doesn't work, right? But up here, when I plugged in negative half and 1 and I tried, right, it has to be multiplied. When I tried it, oh yeah, it does actually work, right? And it works with an eigenvalue of 5. And same thing when I did 1, negative 2, right? So the eigenvalue is lambda. Does the eigenvector have a symbol? Sometimes what we do, that's a great question, Davin. Sometimes what we do is we'll write like v sub lambda, just to remind us that it is actually the eigenvector which goes to lambda. So in this case, we might say like v sub 5, just to tell us that the eigenvalue is 5 here. We might say that that's equal to like 1, negative 2, right? So that's something that sometimes people do, but that's not necessarily universal. A lot of people do it, but not necessarily everyone. Whereas lambda is pretty universal as a symbol for the eigenvalue. Pretty much everybody does that one, right? But there isn't 100% like a set of notation which works for the eigenvector. Okay, I want to do a slightly, yeah, no problem. I want to do a slightly more abstract one, just as kind of like our sending off one. Okay, and we'll see how this one goes. So try this one. And you can imagine like you could kind of compute your way out of this, right? So in theory, if you got this one on a test and it was multiple choice, and obviously that's not going to happen for your test because it's not multiple choice, right? But if you got this on a test, what you could do is find a matrix, like a 2x2 matrix that you know, and test each of these things with that concrete matrix. That's not a good way to get an answer in general, but I mean, if it's multiple choice, who cares how you get the answer, right? Just get your mark. Same thing with like those previous questions, where I said, which one of these vectors is an eigenvector? If it's multiple choice, just, don't find the eigenvectors and eigenvalues from scratch. Just in those cases, we're just asking like, do you know what the definition of an eigenvector is, right? Right, n by n, yeah, it means square, and it means that it could be 2x2, 3x3, 4x4, anything like that, exactly. Whereas if we say n by m, we're generally saying it could really be anything, right? It could be square if it's n by m. It could be square, but it's basically just anything. And in fact, this is an important point, like when we take eigenvalues and eigenvectors, it has to be a square matrix, right? Otherwise, the dimensions just don't work out, because if you want AV to be equal to lambda times V, the input and output vectors there have to have the same dimensions. And the only way that's possible is if A is a square matrix. So you can just try and think about it. If you write down the dimensions of A and V, and you'll see that the only way AV has the same dimensions as V is if A is a square matrix. If the previous, yeah. Well, I mean, it depends what you mean by the previous question, because the previous question is like, I'm wrong, Parker's right, we're both wrong, we're both right. I mean, so that question by, design is necessarily multiple choice. So it kind of depends on what you mean. If it was a multiple choice, like, I'm not certain a way it could have not been multiple choice. Do you know what I mean? Because even if it was just said, if the question even just said who's right, so let's say it didn't like give those options, you still could have done the same thing that I did, right? Which is just plug them in, see that they are both eigenvectors that way, and that would still work without having to find them by hand, right? Does that make sense? Mm-hmm. So the last question is, yeah, it's still definitely doable even if it's not multiple choice. Okay, so I'm going to close this one in about 30 seconds here. I like the, it's fairly random, which means it's good. We're going to learn something with this question. Where you find the eigenvector. Okay, sure, yeah. Yeah, I can do another one like that. Okay. All right, let's take a look. All right, this says we're pretty confused. A and C definitely have the highest turnout, with B and D not that far behind, right? So let's take a look at what this might mean. Okay, by the way, everyone, the correct answer was A. A is the correct answer. So we have A is n by n. And we know that AV equals lambda V. Okay, we're told that, right? That V is an eigenvector for eigenvalue, for the eigenvalue lambda. Okay, that's what we're given. So question A asks, is lambda squared an eigenvalue of A squared with eigenvector V? And the answer is yes. Okay, and I'll show you why the other answers are wrong, but the answer here is yes. And so the reason for this is that A squared V is equal to A times AV. Do you agree, right? Because A squared is A times A, right? Now, AV is equal to lambda V, right? That's this equation, right? AV is equal to lambda V. And I can pull the lambda outside. And when I do that, I get another AV. So I'm going to use that equation again. And I get that, right? So if you look at the first and the last line, what does that say? It says that V is an eigenvector for A squared with eigenvalue lambda squared. Does everyone agree? Does that make sense? Okay. So B says lambda over 2 is an eigenvalue for, so I'm just going to write them as E value, E vector, right? I don't want to write them all out, for 1/2 A with eigenvector 1/2 V. Okay, so let's check that. So I should have then 1/2 A times 1/2 V. So if this is true, this equation has to be true. Right? And wait a second, why isn't this true? This should not be true. Lambda over 2 is an eigenvector. Is this true? So I get 1/4 AV has to be 1/4 lambda V. There's no way that should have worked. Yeah, that's weird. That shouldn't have worked. Or did it work? I mean, the math says it works, right? Did I do something wrong? Because this is true, right? If AV is equal to lambda V, and I multiply both sides by 1/4, that is true. So, what do you mean, can I do that with the coefficients? Yeah, Shanzai, I mean, if you chose and it worked and it ends up being right, it's totally okay. I think it does end up working, actually. You know why? Okay, hold on. I'm going to do some math here. I don't expect you to understand this math. Right? So it says that the eigenvalues of A over 2 are, in fact, the eigenvalues of A divided by 2. And yeah, I guess it works. I can't complain about that. Lambda over 2 is an eigenvalue for, yeah, I guess it works. This is actually pretty nice. This is actually how you do, this is how we make eigenvalue questions, right? So it's slightly more advanced mathematics, but like, I don't know if any of you have actually tried to make an eigenvalue eigenvector question. It's actually really hard. But there is a slight, like as you get into slightly more advanced mathematics, there is a trick to it. But yeah, so okay, I guess it works. So B is also correct. Awesome. Okay, C, so negative lambda. This one better be wrong. Is an eigenvalue for A with E vector negative V sub lambda. Okay, so let's check. So for this to be true, we need A negative V. Right, so here's why this one's not going to work. Negative lambda or V. I guess we've just been calling it V, right? And do you see that this one doesn't work? Because it actually has too many minus signs, right? So on this side, we get negative AV, but on this side, we just get lambda V. And so it doesn't work out because we have too many minus signs. B is always correct. Yeah. I should just do some astrophysics for you. Maybe one day. Maybe that'll be the last one.
You can put it on their final exam as well. Just a question about that.
Absolutely. It's like we covered it in lecture. It's fair game. Is everyone okay with why C doesn't work? Right? Because A times negative V is negative lambda V, but negative lambda negative V is just lambda V. And these two are not going to be equal. Everyone agrees? That makes sense? So C is not correct. All right, put a little X through C. And then for D, we have, sure. So lambda equals 0 is an associated eigenvalue with eigenvector V is equal to 0. That's immediately wrong because remember what I said? So lambda equals 0 is an eigenvalue with E vector V equals 0. Why is this one wrong automatically? Like you don't even need to check? Right, exactly. The eigenvector isn't allowed to be 0. Right? By definition, the eigenvector is not allowed to be the 0 vector. I mentioned that earlier. No, I mean, so it doesn't necessarily make sense to ask if a vector is greater than 0, right, Davin? Right? Like is this vector bigger than 0? Right? It just has to be non-zero, right? Because you don't want it to be the 0 vector. How is A correct? Because if you do this, right, are you comfortable with this math? and are just trying to figure out why this math shows the answer? Or, yeah, Curdy, they can absolutely be negative. They can even be complex, but that's different. So Agam, are you okay with the math here and just why the math tells us that it's correct, or do you need me to go over this math again too? Okay, you don't understand the math. Okay, so basically, for this to be true, what I want to show is that this is true. Do you agree? Right, so lambda squared is an eigenvalue for a squared, right? We're kind of thinking as a squared is the matrix, and lambda squared is the eigenvalue, then this would say that V is an eigenvalue or is an eigenvector for A with the eigenvalue of lambda squared, right? Or do you agree that that's the equation that we want to show for this to be a correct answer? Okay, so what I'm going to do is I'm going to start on this side, A squared V, and I'm going to write that as A times V, right? Because A squared is A times A, right? Now, using the yellow equation above, I'm going to rewrite this as lambda V, right? Because we know by this equation, A times V is lambda V. Right? So far, so good? Okay, so lambda here is just a scalar. I'm going to pull it out. And look, I got another AV. Right? So I'm going to use that equation in the yellow rectangle again to write this as another lambda V, and that gives me lambda squared V, right? So if we check now, this, and we compare it to this, that is what we got. Is that okay? Does that make sense? Okay, cool. And you can see like this pattern would just repeat, right? Like hopefully you can see that in general, if you do this, you'll get this, right? So as you keep, if you take higher and higher powers of n, that corresponds to taking higher and higher powers of the eigenvalues. And again, that's super important, right? That ends up being really, really critical when you do like Markov chains and long-term dynamics for modeling, is that the only eigenvalues which survive are the eigenvalues which are, you know, whose absolute value is bigger than 1, yada, yada, yada. Okay. Can I go over the P lambda equals delta or determinant of A minus lambda I? Sure. So yeah, because this is important, right? You need to understand where this equation comes from. So we want to find, right? We want V and lambda so that A times V is equal to lambda V, right? This is the eigenvalue eigenvector equation. So this is what we want. Now, if I put this on the other side, so that's AV minus lambda V is equal to the 0 vector. And if I factor the V out of this, I would get A minus lambda I, V is equal to 0. Okay, is everyone okay with that? Because some people might not be okay with why the identity matrix is there. But if not, you should say something. Why is the I there? Okay. So we have to think about it. First of all, you can't just factor out the lambda, or you can't just factor out the V, right? This doesn't make sense. We can't write A minus lambda V, because this thing might be an n by n matrix, but this thing is just a number, right? It's 1 by 1. So we can't subtract this, right? Everyone hopefully agrees, right? When two matrices have to be the same size for you to be allowed to subtract them. So I can't just take an n by n matrix and subtract a number from it. That's not allowed. Exactly. The identity matrix is basically acting as a 1. So what we can do is, instead of writing lambda V, let's write that as lambda times the identity matrix times V, right? Because the identity matrix times V is just V. And what this allows me to do is just to actually be able to factor out the V, right? Because the identity matrix is the correct size so that I can do the subtraction between A and lambda I. right? So I've just written V as I times V just so that I can factor the V out. All right, so in fact, I can write that as like an extra step if we want. So A times V minus lambda I times V equals 0. And now I can factor stuff out, A minus lambda I, V equals 0, like so. Okay? Now, and this is the important question. So the original question, but it was sent in a direct message, is can you explain like where the characteristic equation comes from and why is it the determinant of A minus lambda I equals 0? Okay, so certainly the trivial solution always solves this, right? So V equals 0 is always a solution. Right? I think everyone agrees. 0 is always a solution to the homogeneous system. What we need though is we need non-trivial solutions, right? Because eigenvectors are not allowed to be the 0 vector. So we need non-trivial solutions though, right? This is a homogeneous system. So we need non-trivial solutions. If A minus lambda I is invertible, then there are only trivial solutions. There are only trivial solutions. And that's bad, right? So we need A minus lambda I to be non-invertible. A minus lambda I to be non-invertible. And a matrix is invertible if and only if its determinant is not 0. So that means that a matrix is not invertible if its determinant is 0. So thus we need the determinant of A minus lambda I to be equal to 0. Okay, and you might say like, okay, well, why are we going through all this? It's because if I asked you just to find the values of lambda, which make this matrix not invertible, that's a really hard problem, okay? And you can try it, right? Write down an arbitrary matrix and see if you can find, just using that equation, A minus lambda I, the values of lambda which make this invertible. It's very, very hard. The benefit of using the determinant is it just turns it into a polynomial, okay? So the determinant of A minus lambda I is always a polynomial. And we're really good at finding the roots of polynomials, right? Like we know exactly how to do that. So that's why we get this equation that we need to solve for lambda. And so this thing right here is called the characteristic polynomial, which, you know, we often write as P of lambda. Okay, does that make sense? Did that help? Hopefully, yes. Okay, good. Okay, I'm going to try and see if I can find, I think someone asked me for an eigenvalue, eigenvector problem with multiple eigenvalues. Yeah, class is technically over if anyone wants to go. I'm in office hours now. I might just have to make one. Yeah, it went by really, really quickly. I mean, part of it as well was, you know, the eigenvalue eigenvector problems are quite long because they take a lot of time to do, right? All right, I'm just gonna have to make one. Yeah, sure. So let me do one and maybe let me try and do a double thing and do a weird one that has like one eigenvalue but two eigenvectors. I just need to make one really, really quickly because eigenvalue eigenvector problems are not easy to make.
Wasn't there one in the textbook on the notes?
There might be.
I'll try pulling it up while you
Okay.
find something.
Yeah, because the problem is I need to make an invertible 3x3 matrix. I guess I could get away with not. Oh, hey, that worked out. Okay.
Are you trying to get one with one eigenvalue but two eigenvectors?
Yeah.
So you want like a squared, basically?
Not necessarily squared. Hold on, I think I might have just made one.
Okay.
Okay, hopefully this works. Yeah, okay. So hopefully this works. I make no promises. I made this on the fly. Okay, so let's say find the eigenvectors and eigenvalues of this matrix. Let's call it A. So it's going to be 6, 0, -2, 2, 2, -1, 6, 0, -1, like that. Okay, and hopefully this works. So as usual, first thing we do, characteristic polynomial. And don't say I didn't warn you.
It's going to be a messy one.
It is. Okay. So, right, this is A minus lambda I, right? So here's A minus lambda I. I've got to compute the determinant of it. Now, we've got to do this. It's a 3x3 determinant. Let's do it, right? Okay, so I'm going to expand over the first row. Similar to the assignment question. Yeah, maybe. Here, let me take care of this first. So 6.
Why not do maybe potentially the second column because it has 2 zeros?
Oh, you're right. You're right. I should totally do the second column. You're absolutely right. This is definitely going to be way easier, right? Okay, so I'm going to get 2 minus lambda times -1 to the 2 plus 2, right? I'm skipping the first and last one because they're going to be 0 times the determinant of, so if I cross these out, so I'm going to get 6 minus lambda, -2, 6, -1 minus lambda. So this number is just 1. So I'm going to get 2 minus lambda times 6 minus lambda times -1 minus lambda plus 12, right? Okay, and let me write this as negative lambda minus 2. This thing, I'm going to have to just expand it, but I can still do some nice cancellations. So this is going to be lambda minus 6 times lambda plus 1 plus 12. And maybe let's expand the thing inside the brackets, lambda minus 2. So I'm going to get lambda squared minus 5, lambda minus 6 plus 12.
Brandon, it's not minus 12 because you have to do AD minus BC. So 6 times minus 2 is minus 12, and then minus of that is going to be plus 12.
Minus 5 lambda. I really hope this worked out. Is it going to factor nicely, or am I going to have to do magic? -3 and -2, right? Woo! Oh, thank goodness. Usually that doesn't work out nicely.
That's what I meant by a square, because now we have like one of the eigenvalues is squared. That's kind of the case. Okay, I got you.
Okay, so everyone agrees? Like, it's a little bit of work. Actually, most of the time, this is way worse, but I got lucky, and this does work out. So our eigenvalues are 2 and 3. So we've only got 2 eigenvalues. Now, the interesting thing here is actually going to be the eigenvalue or the eigenvectors for 2. Okay, so let's try finding the lambda equals 2 eigenvectors. All right, so what I'm going to do is I'm going to do, remember, I'm trying to solve A minus 2I V equals 0, right? So as an augmented matrix, what is that going to be? That's going to be 4, 0, -2, 2, 0, -1. 6, 0, -3. And hey, do you see what happens?
1, 0, -0.5.
And then everything else is 0. Or I guess here, let me write it as an augmented matrix. Okay, does everyone agree with that? That magically works out? Notice that all the rows are just a scalar multiple of, say, the middle row, right? Row 1 is twice row 2, and row 3 is 3 times row 2, right? So basically, you can move row 2 up to the first row and then divide everything by half if you want to, or divide the top row by 4 and everything cancels out. Should be lambda equals -2 for what, as an eigenvalue? Because no, the only roots here, this is lambda equals 2, this is lambda equals 2, this is lambda equals 3, right? So for lambda to be equal to -2, I'd need a lambda plus 2 to show up in my factorization. Yeah, but this negative sign doesn't affect anything because what I'm going to do, right, is I set this equal to 0. So -0 and 0 don't really make a difference. The only thing that matters is the factors themselves, right? Like try plugging lambda equals -2 into this equation and see if you get 0, right? And what you'll see is, like, remember, this number is going to be 0 if and only if one of the terms are 0. And if you plug lambda equals -2 into this, you would get -4, -4. So negative, -4, -4, -5. That's not 0, right? So I need a lambda plus 2 for that one for that to work. Okay, so I get RREF as this. So I get x1 minus 1/2 x3 is equal to 0. So again, I'm going to set x2 to be a free variable. I'm going to set x3 to be equal to t. And if I solve this, I get x1, x2, x3 is equal to -1/2 t st. So if I factor out s, I get I get 0, 1, 0. If I factor out a t, I get -1/2, 0, 1. So these are my two eigenvectors. And we can check them. Yeah, so exactly. There is another eigenvector for lambda equals 3. But yeah, this is what I wanted to do here was an example and where we actually got two different eigenvectors for the same eigenvalue. Okay, so these are different eigenvectors for lambda equals 2. Should it be positive f? Oh, you're right. It should be positive f. Thank you, Brandon. Yeah, definitely. Just use octave for RREF in this case. Yeah, if you wanted to do it. Usually, though, when you're actually solving for the eigenvectors, the matrix that you get usually falls apart really, really quickly, right? Because by design, you wanted it to be non-invertible. So usually at least one of the rows is a multiple of the others, which means like I didn't need to use octave to row reduce this one. I could do it by inspection because I was like, oh yeah, all the rows are just a multiple of each other, right? But it all comes down to then, solving this homogeneous system, and then the number of eigenvectors you will get is the same as the number of parameters that your infinite solution set has. Okay, and like I said, you can try these. So if you actually wanted to try these eigenvectors, like what would you get? So you get 6, 0, -2. That's not bad, eh? Given that I made this up on the fly.
I was gonna say that's a great question.
Yeah. But again, this is the secret of knowing how to actually make.
Yeah. Actually, I'm not even sure how can you find one off the bat?
Sure.
Do you just test them out, or is there a way to specifically look at them?
Yeah, there's a theorem. So yeah, I'll tell you in a second. It's very, very cool. And then what's the other one? 1/2, 0, 1. Let's use 1, 0, 2, right? I think that's just better. So let's just not have fractions. So if I do that, I'm going to get 6 minus 4, which is 2. 2 minus 2, which is 0. 6 minus 2, which is 4. And yep, that's 2 times 1, 0, 2. right? So these two vectors are not multiples of each other, but are both eigenvectors for lambda equals 2, right? So yeah. And does that make sense? Whoever asked it, who wanted that, Ali, is that good for you? Did you see how we made that work? Like, it's a lot of work, right? Like these aren't a quick and easy thing. They take a bit of time, but this is, and of course there is still the lambda equals 3 eigenvectors that I didn't do. So if you want, that'd be a great thing to try for yourself. And I know what the answer is. So what you could do is you could try it right now, and I could tell you if you get the right answer. Yeah, so why don't you try it? Try the lambda equals 3 eigenvector. Here, you know what? I'll write the answer on the side. I think the eigenvector is 213.
I'm actually mostly curious about how you came up with like a question that has like on the spot.
Okay, so if a matrix has a linearly independent, I'm gonna say math words to Aziz now, so don't freak out. So if a matrix admits an eigenbasis for the space, right? So if all of the eigenvectors are linearly independent, then you can diagonalize your matrix, right? So you can write it as P, D, P inverse.
Yep.
And so P are the eigenvectors, and D are the diagonals.
Correct.
So what I did, so first of all, when you make an eigenvector eigenvalue problem, you just work in reverse. So you decide what you want your eigenvectors to be, and you put them in the matrix P, and you decide what you want your eigenvector or eigenvalues to be, and you put them in D. And so when I chose D, I specifically chose one that had a repeated eigenvalue. And then that's, so that's how
I see where you did that with the reverse. This also helps when you're also raising like the matrix to power of something, right? Like
exactly.
Okay, I see what you did.
Yeah. So this is like, this is one of the fun things about being an instructor is you have to use the math that you know to try and reverse engineer it to make problems instead of just solving them. So yeah, that's the answer there, is to use diagonalization.
Yeah, that makes sense now. I forgot about that for a second, but I'm back in business here. I got you.
Yeah, the only thing you have to worry about there is that the P inverse can be so nasty that
that's what it is, right?
Yeah. Right. So when I was saying I got lucky is that the P that I chose, right, with these eigenvalues ended up having an integer inverse. Like the inverses didn't have any fractions. And so I was just like, boom, we're in money, right? I just multiply these together and figure out what A is.
It'll be tricky because the characteristic polynomial in that case would be very tricky, right? Like if the numbers weren't nice on the P inverse.
Well, there's a hack you can do though, in the sense that like once you've computed P inverse, find the biggest fraction, right? Like let's say, and multiply by that.
The lowest common denominator type of stuff.
Yeah, basically. And it has the effect of scaling all of your eigenvalues. So all of your eigenvalues will get bigger. So you can, instead of having eigenvalues of like 2 and 3, you'll have eigenvectors of like 24 and 30. But the numbers work out nicer because at least they stay integers.
No, I see it. Okay, makes sense.
Okay, now somebody was asking for a question like the assignment. And so, yeah, this is an important one. So what I keep recommending that people do is, do this. I don't know. I think the question was just, can you do something like the assignment? But let me double check. Yeah, just as similar to the assignment. Okay. So if we do this, what do we get? Everyone? Okay, yeah, sure. So this is like STU. I guess this is like part 1. So maybe we should do something else. Okay, here, let's not do this one. Let's do -2001 times A, B, C, D. Okay, so if I do this, what do I get?
Also,
Abby, you were absolutely right. It gets swapped, and that was what I was going for. But that was like a hint for part 1, right? Yeah, beautiful. Okay, good job, Brandon. So we get -2A, negative 2b, c, and d, right? So this was the same thing as having performed
Because this is also kind of like a hint, but it's very funny to watch.
Yeah, right. Like this is a huge hit. Negative 2 row 1 into row 1. Right? Does everyone agree? Yeah,
Actually,
Brandon, I knew because I know you know the answer because right from last time, and I was wondering if you even did the calculation or if you just knew what the answer was and so just wrote it down.
it's actually funny because like us TAs, we don't know what the answer is theoretically. I know the answer because I read the assignment and I solved it like on my own, but we don't even get the answers beforehand. So I'm in the same boat as you guys most of the time here.
That's right. But you're TA for a reason, right?
Yeah,
that's a great answer.
That is a great point as well.
Right. Oh yeah, okay, yeah. I mean, like, that works too. I think there's value in that. So this, so direct messenger, do you see what just happened here? This matrix, this is U1 negative 2 for the 2 by 2 matrices, right? It performed, when I multiplied on the left, it performed this row operation to the matrix, right? So this ends up often being kind of a critical thing. Like, one, does this make sense? And two, can you figure out how to generalize this to the 3 by 3 case? Aiden, yes. And then Avi, yes. Yeah, that is precisely how I do it. And Abby, that doesn't even need to be a direct message. Like, that's not an academic offense. Explicitly, we are trying to get you to emulate row reduction using matrix multiplication. And that is a beautiful and perfect way of summarizing what the assignment is trying to do this. Yeah. Okay, so by definition, if you look at what U1 negative 2 does, in the assignment, it says U1 negative 2A should be the matrix A after you've performed this operation. Right? Like, do you have the assignment in front of you? And do you notice how the assignment says UIC should be the matrix A after I've applied the operation CRI goes to RI. So if I plug in the values of C and I in this case, U1 negative 2 is the matrix A, or U1 negative 2 times A should perform the row operation negative 2 row 1 into row 1, right? Okay, so what you're trying to do is figure out a way of, and to just exactly phrase what Abby said, you're trying to figure out a way to emulate this row reduction with matrix multiplication instead. So instead of doing row reduction, you're trying to say, are there a set of matrices that I can use such that if I multiply them, it does the same thing as the row operation, right?
I really like that question number one. I think it's very eye-opening, at least to see how matrices work together.
Yeah, it's very, very nice. And it kind of depends on what you mean, because what you've written down is implicitly a 2 by 2 matrix. And so you probably, it depends on what you mean by putting it in a 3 by 3.
I think question 5 is just asking you to perform specific, I'm assuming part 5 of that numeracy 1 question. It's just assuming it's giving you specific instruction on specific multiplications you need to do by matrix A to see how that will look like at the end. I think for part 5, you don't have to expand. It's part 6 where you need to expand it.
Yeah, yeah, exactly. Yeah.
Okay.
Yeah, and I'm still not certain what you mean, because you can't put the 2 by 2 identity in the 3 by 3 matrix. Oh, in your matrix A. No, A has to be arbitrary. Yeah, A has to be an arbitrary matrix. You can't set any of the numbers in it. Okay, it's got to be like this, right? It's got to be like A, B, C, D, E, F, G, H, I.
Yeah, Christian, that's correct. And for Jack, yeah, I get you. Like, one thing is, once you see how one of them works, at least I personally, for that question 1, once you figure out the first one, I feel like, and actually understand what's happening, the rest become very systematic after that.
Yeah, and I mean, like Jack, I actually love to hear that, which is like you grinded out the answer, and then once you had it, you were like, boom, I've got it, right? Like that's phenomenal. That's exactly what I want. Like once you have that, those are the sorts of assignments that like that's exactly what I want to happen, right? Is that you think deeply and carefully about a question for a long time, and then suddenly everything clicks and makes sense. So the sort of epiphany that you had there is, you know, just the dream of an instructor. Like that's exactly what I wanted to happen. So phenomenal. I'm very happy that it happened for you. Yeah, and I mean, like, you know, so I got a direct message saying I wouldn't have gotten it if I didn't get the hit about identity matrices, and that's okay, right? Like, we're fine giving you hints. That's why I kind of really alluded to, I think last Thursday, I said, you know, make sure that you start this one early because you're going to have questions about it, and you know, ask your questions, right?
Yeah, no, the first time you read it, especially because the way it's worded, it's kind of tricky a little bit. The first time you read it, it hits you at once and you're kind of confused. But when you break it down slowly, I think it gets better very quickly than others.
Yeah, exactly. And Brandon, that's a great question. And yeah, share that kind of like learning thing with your classmates, because that's exactly what we want to see, right? Like, what do identity matrices do? Like, how do they work? Why do they work? And once you realize that, you're just like, oh, okay, this is exactly what I want, right? I can't, certainly you can use zeros and ones and C's. So, and maybe that's not satisfying, but definitely you can use 0 and 1, right? Like you're definitely allowed to use those numbers. Instead of giving specific answers, we can, yeah, I mean, like, it depends on what you mean by general process, but like, yeah, you should be able to describe the matrix because there is a matrix which works, right? Like if I said to you, give me 2, 3, 7, you should be able to write down exactly what that matrix is. But of course you don't want to do this for all 6 options and you know, the infinite values of C. So what you can say is, you know, TIJC is a matrix with zeros here and ones here and C's here, right? And that's totally fine. That's okay. You can use sentences. No, I think like in terms of a writing thing, Brandon, like giving a general description and then giving an example is probably the best way that you can do, right? Like, and then, yeah, if you add some other things too, it doesn't hurt. I mean, especially if it helps you solidify and organize the information in your brain, I don't think there's anything wrong with that whatsoever.
Mm-hmm.
Okay, everyone, just give me a second to duck off. I'm just gonna like fill my water and stuff, but I'll be back in like, you know, 30 seconds.
I mean, I'll still be here if you guys want to ask any questions. How's life, guys? It's going. Busy, but it's going. I got a private question asking about part 5. So for part 5, you have to kind of put the basically you have to put a bunch of matrix multiplications next to each other. There's 4 matrix multiplications and then A itself. So there's 5 matrices multiplied by each other. If it's yours, they won't be removed in person. The tutorial, I'm pretty sure that the tutorials for this course are all going to be online. So for this course specifically, the tutorials are going to be online. I know a lot of your other courses, maybe they're switching to in person, but for this one, it's going to be online. I got another question about part 5. I thought there were only going to be 3 because it's from parts 1 to 3. Well, if you notice, I think in question 5, it uses the U matrix twice. There's 2 different applications of U. So you're going to have, for each one is going to be 1 matrix, right? So I think it was like U of 2 bracket 3 and then U of 3 bracket minus 1. Those are like, you're doing 2 operations of U, but like with different numbers. So each one of them is 1 matrix. And then you have the T the T operation, that's one matrix, and then the S operation, that's one matrix. So in total, you have 4 matrices multiplied by each other, and then all multiplied by that A. So in total, you're going to have 5 matrices. 4, which is your row operation that you're going to actually have to work for and solve for, and then just A at the end, which is the 5th one. And for question 5, they're not asking you to simplify, you just have to kind of list them out, like multiply them all by each other. Well, Tyler's resetting his laptop so he can join Zoom again, but so again, another question about part 5. You're going to use basically the same relative equations that you, or matrices that you got in parts 1, 2, 3, that logic. We have to like apply the specific numbers in example 5. So you're going to get like 4 matrices multiplied based on the ones you got above, that general formulas you got above. You plug in the specific numbers for part 5, and you should get 4 different matrices for each one of the operations. There's 2 for U, 1 for the first U, one for the second U, 1 for the T, and 1 for the S. And then they're all going to be multiplied by the A. So it's going to be like, again, 5 matrices all multiplied by each other. How to do the last question. So the example gives the equation.
How do you do this without giving it away?
Right. For question, also just kind of one last thing about question 5. That one, because I have like 3 direct messages about that. That specific example they give at the bottom is what you're supposed to be filling. That U2 bracket 3, U3 bracket 1, and so on. That's what you're trying to actually solve for that.
Yeah, you don't want to use sigma because there's no sums involved. But yeah, think about it like this: like your yeah, okay, maybe here's a hint that might work. A to the 7 over A cubed is equal to A to the 4. Right? Do you agree? Like A, that's A to the 7 divided by A divided by A to the 4. Or I guess A to the 3, whatever. Here, let me get rid of one of these. Does that help? Cool. And for yeah, and like if you when you create your arbitrary matrix, you can just keep using that same one. Like, you know how I wrote up here, like this matrix A, B, C, D, yada, yada, yada. Like you can just use that same arbitrary matrix throughout if you want to. That's totally okay. Mm-hmm. Curdy. So Curdy, that's just an example, right? Like don't necessarily use that one. But like those are like in that scenario, those row operations were performed to A, and then we replace those row operations with those matrices. And in question 5, I just want you to write out the row operations as matrices, and that's it, right? So you know that there's this correspondence between matrices and row operations, and all I want you to do is when you did the row reduction, so now replace the row reduction with the matrices which do the row operations. And Brandon, yeah, that seems fine. So in like you should be able to, so for like the S's, you can just write them down. There's only 3 of them. So if you just want to write all of them down, you can. For the T's and the U's, again, I think the best way to do this is to say T is a matrix that has 1s here, 0s here, and like C's here, sort of thing, right? Like you can just say where they are and then maybe give an example, right? Like, so earlier above I said, for example, T37 is this matrix. And, because the ones are here, the zeros are here, and the 7 is here. So that sort of thing, like that's how you should describe them instead of writing them all down. Now, if you want to, there's only 6 of them, right? If you let C be general, there's only 6 of them. So you could just write all 6 of them down if you really wanted to. Curdy, yes, exactly. Yeah. You mean your row operations vary from somebody else's? Yes, that is very possible. No problem. Okay, anyone else? Otherwise, I think we can, and we don't multiply it, we just show it, right? And in the next step, you actually do the multiplication. Yeah, I mean, that said, though, if you want, you can like go into Octave and check, right? Because exactly, yeah, without A. But you can go into Octave and you can be like, you know what you did at each step of your row reduction, and you can check if you got the right matrices by checking whether or not once you do all these multiplications, you get those matrices that you should have gotten in your row reduction. So that's something you could do. We don't want you to do it for the assignment per se, but you could do that into Octave and check, right? That's something you could do. What makes the row operations into matrices? So by definition, each matrix performs a row operation. Okay, so for the person who said for part 5, you make the row operations into matrices, you actually did that in parts 1, 2, and 3. So in parts 1, 2, and 3, you found matrices which performed the row operations. In part 4, you actually row reduced the usual way. In part 5, you replace the row operations with the matrices you found in parts 1, 2, and 3. When multiplying matrix for part 6 in question 1A4, do we start from matrix multiplication from the right? It doesn't matter. Matrix multiplication is associative, which means that it doesn't matter whether you do, so when you're multiplying matrices and you've got like 3 matrices like this, you could start on the left and then do the right, or you could start on the right. It doesn't matter. But importantly, when you apply the row operation, the row operations go in this direction, right? So if I write ABC times X, let's say X is what I'm row reducing, then what I'm saying here, C was the first operation I performed, B was the second, and A was the third, right? So in that sense, they go right to left. But in terms of multiplying them, you can multiply them in any order because matrix multiplication is what's said to be associative. That's what that property is called. Okay. For 1.6, I computed with Octave. Yeah, that's totally fine. For 1.5, I only used TIJs. That's totally fine. Yeah, I think our solution also actually only used TIJ, but we couldn't guarantee that any, like, some people definitely, I think, used U's and some people used S's. So they're all there though, so it's totally fine. But yeah, we only used TIJ when we did our solution too. For part 1, couldn't there be many matrices since you can choose whatever rows to flip? Yes, there are. So there are actually 3 matrices for Sij, right? There is S12, S13, and S23. And then you note S21 and S12 are the same, right? Like if I say flip rows 1 and 2, that's the same thing as flipping rows 2 and 1. So those are the same. And this is the same. And this is the same, right? So you don't have to compute these ones. There's only 3 that you have to compute. For the T's, there's 6 because T21 is different than T12. So you actually have to compute all of those. Sure, and if you want to start from the right, but like I said, it doesn't matter. You can do whatever you want, right? Let's see. Yeah, Christian, that's perfectly fine. Yeah, that's the right idea. I don't know if I mentioned T anywhere, Curdy.
No, because for the second part in question 1, I only had to do one TIJ. I didn't know that we had to do like all 6 of them.
No. I mean, like if you can describe Tij for any I and J, that's fine. But if you write them all down explicitly, you have to write them all down. Does that make sense?
Mm-hmm. I would say the general form is easier to write than writing them all down.
Yeah, like I wouldn't write them down. And not only that, like once you've written down like 3 of the 6, you're like, oh, okay, this follows a pretty clear pattern, I think, right?
Agreed.
So then for question 5, you only want the main ones that we found, or do you want all of them? Just the ones that you used in your row reduction, right? So you perform some row reduction, whatever, it doesn't have to be the same as ours. Then repeat that row reduction, but now using the matrices, and just write them down. Yeah, and Abby, exactly. That's a great way of putting it. I wrote a general description for the others, but computed one. Yeah, that's okay. Yeah, exactly. Yeah, that's perfectly fine. Okay. If we only do 3 Tij and conclude that it's showing a pattern, yeah, I mean, that's okay, but then you still have to describe the whole pattern to us, right? And so like, if you write down 1 and describe the pattern, that's fine. If you want to do 3 and the pattern, that's fine. Just make it clear that you're not stopping at 3, because it's kind of a weird place to stop. Just make it clear like, oh, I see a pattern now. Here's the general pattern for the rest of them, right? So you just make sure you really clearly communicate that. Because remember, TAs tend to like go through your assignment really, really quickly. So you want to make sure that they don't see those 3 and then think that you stopped, right? You really want to make it clear that there was a more general formula. Otherwise, Aziz is going to get a remark request. So he doesn't want you to do that either.
Yes, please. I'm up to my nose with the remark requests. I got another 10 yesterday.
Oh, geez. These people.
I don't know why, for this specific last assignment, I've gotten the most amount of regrade requests I think ever. Really, I've gotten like I think close to 60 of them.
Are they all the same question and the same thing?
No, they've been kind of like a mixed batch, to be honest with you. Most of them I've rejected, but like it's more like complaining and asking for marks, like just begging for marks more than having like a
solid argument.
A legitimate reason for it.
Yeah, I mean, in those cases, just read the argument, and if it's clearly not valid, just reject out of hand.
Yeah, I always like try to like go into it, just see maybe like if there's something in there, but like more often than not, the answer is no.
Right. Well, then in that case, you can deduct marks. Right? Take more marks off.
I could.
It's got to be. It says right in the thing, like it has to be a valid reason, right? Like people.
I strongly agree with you, because some of the reasons I got were very, I'd say, for lack of a better term, questionable.
Yeah, like the remark instruction says, do not beg for marks. That is not. It has to be the TA made a mistake, right? Like,
I'll tell you, there isn't many of them that got like. Some of them I understand why they asked for a remark, even if they didn't get it. I get the logic behind your question, please. But some I look at them and I'm like, I don't even get the logic behind your question. So like, that's what.
Yeah.
Kind of.
We did once have a student get like really upset because she didn't do well. I don't know. I probably told you the story. It was, oh man, who was the TA it happened to? But anyway, she insisted because she tried it, she should have at least gotten 50%. Like, I think this is a term test. She's like, I sat down and I wrote it. I should at least get 50% just for effort. I said, no, that's not how that works. And then she got really upset and like really started to, like throw stuff around and stuff. Anyway, so we should write the matrices with variables and then explain one scenario that works where we would say these spots there are zeros. I mean, like, no, don't write them with variables. You can almost write all of them out explicitly, right? Like, in fact, for like the U's, there's only 3. For the S's, there's only 3. For the T's, there are 6. And there should almost be no variables. The only variable that should appear in the U and T is C, right? Because you don't know what C is. So that's the only variable that should appear in those ones. Other than that, though, you can just describe them, like write one of them down explicitly, be like, this is T2C, T12C, and then, describe the rest of them.
Okay, I don't think that matters that much.
The general
for constants.
Oh yeah, it doesn't matter. Use whatever you like. The general matrices which are used to perform the row reductions are all going to be multiplied. Yes. Well, they like in the sense that they might not all appear. The ones that appear will depend on how you actually row reduced A. And we don't know how you did it, right? Because there's more than one way of doing it. So some of them might appear, some of them might not appear at all. Like there's no guarantee that they'll all show up. For 335B.
I just opened the question here.
Okay. True or false, V lambda is an eigenvector of A and A is invertible. Yeah, so that is true. Oh, so if A V equals lambda V, and so you're told A is invertible, right? So multiply A inverse onto both sides. So this side just becomes the identity. So you get V is equal to A inverse lambda V. Now put lambda on the other side. So you would get, I don't know why my eraser isn't working. 1 over lambda V is equal to A inverse V. And that is precisely the statement of the question. Right? So 1 over lambda is an eigenvalue for A inverse with eigenvector V. And you might say, well, like, how do I know lambda is not 0? In which case, if you're asking that question, that's phenomenal, and try and figure it out for yourself. But yeah, if you're invertible, none of your eigenvalues are 0.
That makes sense.
And yes, it is, but you might want to write that out explicitly from your direct message from a bit ago. For you, I said for a general explanation. Brandon, specify your column too, though, right? You can't just specify, oh no, where you said the blank in the blank is replaced by, yeah, that's fine. That's totally fine. I think that's clear. Yeah. Curdy, so T12 of, let's say 7 performs the row operation like that. T21 is different. Right? These are different row operations. And it's true that is that operation, like, because it doesn't matter what number you put into the F, right? So yeah, that it is true. It is still that operation.
Okay.
Okay, Curdy, you're good. That makes sense. You understand why those are different? Why T12 and T21 are not the same? Okay, cool. All right, everyone, is that okay? We're done because we are at 7 o'clock now, but hopefully I managed to answer the best of it. Okay. Yeah, thanks, everyone. I can't hang around for too often just because, you know, the 24-hour test. You don't have yours this week, but I have other classes that do. So I actually need to get them set up. But yeah, absolutely. Have a great weekend, everyone. Work hard on that assignment. Make sure you get it done. We'll still hang around Piazza and stuff. And otherwise, I will see you all on Tuesday. Thanks so much. And yeah, see you later, everyone.
See you, Tyler.
See you, Aziz.